In this video, we're going to discuss a mathematical process known as Hess's law. If you recall, the second half of this unit on thermodynamics is all about methods of getting delta H values. We've already talked about a way of measuring delta H values using calorimetry. Hess's law is one of the first tools we'll use then to calculate delta H values. This is assuming you already have data present, and then you can use that data to calculate it as opposed to making unique new measurements. Let's start by going over some learning objectives in this video. We're going to review the concept of measuring versus calculating delta H really quickly to make sure that you're keeping track of the different tools we can use to get delta H values. Then we're going to dive into this new process known as Hess's law. We'll start by talking about the scientist himself, Germain Hess. We'll then go into the idea of what a state function is. State functions are something you've been working with probably for a while now. You just didn't realize they were called state functions. We'll define the term and identify certain characteristics that can be described as state functions. Hess's law then takes advantage of the fact that enthalpy is a state function, and it uses that concept to take the enthalpy data from other chemical reactions and using it to predict the enthalpy of your chemical reaction that you're currently interested in. We'll of course then wrap that up with an example where we'll go through two problems, one of which is very simple, one of which is a little more complex. We'll obviously continue the practice in the example process in class to give you guys a really good feel for how this mathematics really works. Now let's start by recapping some of the ways we can get this delta H value. If you recall, delta H is the amount of heat energy absorbed or released per amount of chemical used in any chemical or physical process. There's a lot of different ways to get this. The way we spent some time on already and done some lab work with is the concept of calorimetry. And on the right side of the screen there we have a picture of a calorimeter. You run your reaction inside of the calorimeter, the temperature changes based on what happens in the reaction, and as a result we can use some mathematics to calculate values of delta H as a result of that. At some point, this is always what needs to be done. The only way you can get real new data is by making these types of measurements. However, if you already have data that you've collected on many different types of reactions or many different types of processes, you can use that data in order to then calculate the delta H of a new reaction. This saves you then the trouble of actually having to step into the lab. You can just do some math on some paper as opposed to getting out all the equipment. Now there's a lot of different ways to calculate or estimate values of delta H for certain reactions. One of which we'll talk about later on down the road is the concept of bond enthalpies. In a chemical reaction, bonds are broken and bonds are formed. The energy from the bonds broken is then used to form the bonds on the other side, and any differences in the amount of energy broken versus formed can translate into a delta H value. We can make this kind of one step higher in complexity. We can use heats of formation. Instead of focusing on individual bonds, we can look at what chemicals are being formed and what chemicals are being broken down. Every chemical formed costs a little bit of energy. Every chemical broken down releases a little bit of energy. We can look up data on what are known as heats of formation for each substance and use that to estimate the delta H. We can look at the chemicals in the reactants and the chemicals in the products and find differences in energies. Again, heats of formation is something we'll tackle a little further on down the road. Our third method then for calculating delta H is the one we're actually interested in today, and that is Hess's law. In Hess's law, we get the delta H from the enthalpies of other similar chemical reactions. And we use those enthalpies, combine them in a special way, which is what Hess's law is all about, and it allows us to calculate the delta H of our new unknown reaction. The important thing to note with all three of these, it's all the same general concept. Here we're focusing on the energies in the bonds. Here we're focusing on the energies in the substance as a whole. And here we're focusing on the energy of the whole entire reaction. But in each case, we're taking the amount of energy before and subtracting it from the amount of energy afterwards. And the end result is a change in energy, which is our delta H value. This then brings us to the topic of the day, which is Hess's law, and before we can get into it, we should talk a little bit about the scientist himself, Germain Hess. Germain Hess was born August 7th, 1802. We have a picture over there on the right side of the screen. He was a Swiss-born Russian scientist, so he's native to Russia but born in Switzerland. He received his first round of education from the University of Tartu. I believe that is in Russia. I believe shortly in the early half of his life he migrated back to Russia. And he was originally trained as a doctor. He was trained in medicine, and he actually received a license to practice medicine. During his time, however, while practicing medicine, he met up with a Swiss scientist based on his Swiss ties, and that got him interested in the research in chemistry. He went back to school to the Stockholm University back over in Switzerland, and then received a second degree in chemistry. Ultimately, this led to him being a professor at St. Petersburg Technical Institute, again back in Russia now as he went home with his family. Neat thing about Germain Hess, he was pre-Nobel Prizes, so he did not receive a Nobel Prize for his work, but his work was dealing with research in thermodynamics, and he was looking at series of chemical reactions that happen step one, and then the next reaction happens, and the next reaction. Each step is based off of the products of the previous one. Like I said, he didn't receive a Nobel Prize for this work, but the interesting thing is that his work here, the idea of Hess's law, eventually led to something we now know as the first law of thermodynamics. And just like we have Newton's laws from last year in physics, the laws of thermodynamics have a similar amount of magnitude and importance in the world of chemistry. So no Nobel Prize, but certainly a very high honor to be bestowed upon Germain Hess. Last but not least, in his later life, he did a lot of work dealing with minerals and some geology, and as a result, there was actually a mineral eventually named after him, Hessite, which is actually silver telluride. So just a little fun fact about Germain Hess. So Hess's work in thermodynamics was based off the concept of state functions. Certain variables or certain concepts in chemistry can be described as a state function. We need to take some time right now and identify what a state function is, and then we'll translate that information into how state functions are important for calculating delta H values. So let's start with the definition. A state function is a property of a system that depends only on the current state of the system, not on the way in which that state was acquired. And the key term you want to keep track of here, the idea you want to focus on, is the idea that state functions basically are any characteristic, any measurement that is independent of path, meaning it doesn't matter how we got to where we are, the measurement is only dependent on where we currently are. Now that might seem a little bit mysterious at this point in the game. Let's get some examples of what state functions are first, and then we'll talk about an example of something that's not so chemistry that hopefully make things get a little clearer. So some state functions that might look a little familiar from this chapter. We start with dealing with these values here. Delta E, any change in energy is always considered a state function. The amount of energy we have now is not necessarily dependent on how much energy we had before. U stands for eternal energy, and delta H is the one we're more familiar with. This is our enthalpy. So these are the values we've already tackled in this chapter, all three of which are state functions. Things to come we'll be dealing with later in the chapter is the value of delta S, which is entropy, and delta G, which is known as Gibbs free energy. Entropy is a measurement of disorder in a system, and Gibbs free energy is a tool we use to predict the spontaneity of a reaction. Does the reaction happen on its own, or does it require a push from an outside energy source? All of which, by the way, state functions. Now these functions are a little bit less familiar with us. We've only been dealing with them for a little while. Some things you might be more comfortable with are the concepts over here on the right. Mass is a state function. Pressure is a state function. Temperature and volume. A great example is the temperature in the room right now that I'm sitting in is 74 degrees. That measurement of 74 degrees doesn't matter that the night before, the temperature in the room was probably 65 degrees. It has no bearing on the current measurement of the temperature, making temperature independent. The temperature we have now is independent of how we actually got there. That 74 degrees is an independent measurement. Now, because state functions can be a little bit difficult to keep track of, one of the things I like to do to explain state functions is to use a map such as this. And we can imagine that we're taking some sort of road trip. Let's say, for example, we start over here in Boston, where we are now, and we end up wanting to take a road trip over here to Sacramento, California. A couple different ways we can make that road trip. One of those ways would be taking a direct route. And on that direct route, we would use, if we were driving, say for example, although it would be difficult to drive through some of these areas, if we were driving, we would use a certain quantity of fuel, we would get a certain mileage, we would travel a certain distance, etc., etc. And that would be one way of traveling from here all the way over to Sacramento. Another way of traveling from here would be to take somewhat of a long way around to visit maybe some places along the way. Say we go from Boston, and then first trip we drive down here to Richmond. Second part of our trip we drive over here to Atlanta, Georgia. Maybe from Atlanta, Georgia we go all the way up here to Topeka, Kansas. Then we head all the way down to Austin to visit some family. And then maybe from Austin we get tired of sitting in the car, so we drive all the way over here to Sacramento. So we have our short way of traveling on this trip, and we have our long way of traveling on this trip. And then we can talk about these two different trips, two different paths that we've taken to get from Boston to Sacramento, and talk about things in terms of state functions. So for example, we could talk about miles traveled. So the question at hand, would miles traveled be a state function? Does the amount of miles we travel have anything to do with the path we took? Well, it most certainly does. We would expect to travel fewer miles on the short path and more miles on the long path. So we would not say that miles traveled is a state function. Likewise, we could talk about the time it took us to get there. We would certainly expect it to take longer amounts of time on this path than it would take to get on this path, and as a result of that, we would not think of time as being a state function in this context. One thing we can talk about is the actual destination. Well, in both cases, our destination was Sacramento. We got to Sacramento taking the short trip. We got to Sacramento taking the long trip. Destination is something that I would describe as a state function. And if you want one more example, we could talk about something like, for example, the mileage that we record in our car, the fuel economy of our car. Well, assuming this one trip is not more or less hillier than the other, the fuel economy going the short way would be the same as the fuel economy going the long way. That measurement wouldn't care which path we took, so again, mileage would be an example of something that I would describe as a state function. So again, the real key here for state functions are things that are the same measurement regardless of how you get to them. Short trip versus long trip doesn't affect the measurement. You're dealing with something that's a state function. How then do state functions come into play when we're dealing with Hess's law? Well, to get into that, let's start with a quick definition of what Hess's law is all about. And what Hess's law basically says is that a chemical reaction run in one step has the same delta H, the same enthalpy, as a reaction run over many steps. And this is only true as long as they both have the same starting reactants and the same ending products. This is the same as saying they both start in Boston and end in Sacramento. As long as we have the same starting and ending point, our delta H value should be independent of the path we took to get there. So that's exactly what we have in the next step here. Delta H is independent of how many steps it takes to get our particular chemical reaction done. And we can actually demonstrate this with a fake reaction here on the bottom. Let's say our chemical reaction has reactant A reacting to form chemical Z, and the delta H of this entire process is 10. We can show this reaction happening over many steps. Notice here we start with reactant A and it forms chemical B. Chemical B is then used in another reaction to form chemical C, and chemical C is then used in another reaction ultimately to form chemical Z. So notice we have the same starting point and the same ending point as our original reaction. And if we look at the three delta H's of these things, they add up to 4 plus 3 plus 3, which gives us a delta H for the overall process of 10, which matches the delta H we originally had here. Here's the reaction in one step, here's the same reaction in 3 steps, and the overall delta H is the same. Likewise, we can do it over here too. Let's skip a step here. Instead of going from A to B, let's go all the way from chemical A to C, and then we'll have the same reaction down here where chemical C reacts to make chemical Z, and again we notice we still have the same starting and end points, and again our delta H's for the entire process add up to 10. So the real philosophy here is that if we can find a way to add our reactions together so that they match the target reaction up here, then we can find also a way to add the delta H's together to determine. And that's really what this process is about, is determining new delta H values. So you can almost imagine this reaction here is new, these reaction here were already known, and we can use this data in order to determine this data up here, the new delta H. So just to put all that into words, delta H then, this Hess's law concept, is used to calculate the delta H of an unknown reaction, which we'll be calling the target reaction from now on, given the delta H of other known similar reactions. And the other reactions we're going to refer to as data reactions. So our job is going to be to find a way to combine the data reactions so that they match up to the target. And that's exactly what we have written down here. Find a way to combine those data reactions in a way so that you have the same overall reactants and products as what you see in the actual target reaction. Let's dive right into an example of how this process works. This example is very simple. It simply involves the basics of the idea. Most problems would be a little bit more complicated than this. Let's say, for example, we want to take a look at a target reaction where carbon in the form of graphite, which is what you find in your pencil, is turned into carbon in diamond. And we can, if we didn't already know, the carbon in diamond is the same as the carbon in graphite. It's the same as the carbon in coal. They're just arranged in different ways. These are known as allotropes. Anyway, if we want to convert from one type to another, which by the way would be very handy-dandy, right? We want to figure out the delta H of this process. And that's again what our target here is, determining the delta H of this reaction. Well, to figure out that delta H, we're given data on other reactions. And notice how these reactions contain similar chemicals, similar products and reactants. And we're going to find a way to combine these reactions so that they end up looking like this one. Well, the important thing to do is to identify the chemicals that we're looking for. Here's carbon in its graphite form acting as a reactant, which is what we want it to be, right? And here's carbon in its diamond form acting as a product, which is what we want it to be. If you feel like you've got chemicals lined up so that all the reactants and all the products are in the right place, we can test that by combining the two reactions together. And if we do things right, they'll combine in a way that makes the target reaction. So when we combine these two, I've highlighted the two chemicals we're interested in red. We get them in the right place, but we also have all these other chemicals kicking around, and we don't want them there because we want our reaction from our data to look the same as our target. Well, it's important to notice here that we've got carbon dioxide as a reactant and carbon dioxide as a product. If they're on both sides of the reaction, that means they didn't react and we can cross them out, which means we can do exactly the same thing with oxygen. We have oxygen on both sides, and when we're done, all we're left with is the target reaction we're looking for, graphite turning into diamond. So we've found a way then to combine these two reactions so they match our target reaction, but that's not the answer. That doesn't do much for us. What we were interested in the beginning was the delta H's. Well, as you might imagine, since delta H is a state function, if I can add the reactions together in 2 steps instead of 1, I should also be able to add the delta H values together and get a delta H for this overall process. And that's exactly what we end up doing. The delta H for the first reaction plus the delta H for the second reaction gives us ultimately the delta H for our new reaction, which is positive 1.9 kilojoules for every mole of carbon reacted. So we've combined data reactions in a way that allows us ultimately to get them to match the target reaction. If the data reactions can match the target, then the delta H's can match as well simply by adding them together. And that's the general concept behind Hess's law. It's finding a way to combine data reactions to match a target. Now, unfortunately, not all situations are quite as simple as that. Reactions usually do not combine in such easy ways to immediately get you to the answer you're looking for. So we don't normally get this simple form of combination. Typically what we need to do is manipulate our data reactions to make them match the target reaction. And we can do this in a couple different ways. First of all, we can reverse the direction of any chemical reaction that we want. If it's happening in one way and we want chemicals in different places, we can reverse that direction. The important thing to note is that whatever you do to the reaction, you do the same exact thing to the delta H value. So if you reverse the direction of the reaction, you're also going to reverse the value of delta H. Basically meaning you're going to change from the positive to the negative or from the negative to the positive. We can also manipulate our reactions by multiplying the entire reaction by a constant multiple. For example, we could take all the chemicals in a reaction and double them, all the chemicals in a reaction and triple them, or all the chemicals in a reaction and halve them. The philosophy here being is if our target reaction has multiple of a certain chemical and our data reaction only has one, we can double or triple to get those numbers to match. Just like before, the key thing to keep in mind is whatever we do to the actual reaction, we do the same thing to the delta H. So for example, if we double our reaction, we double delta H. If we have our reaction, we have our delta H value. Again, both of these tricks, kind of in summary here, are basically tools that we can use to manipulate our data reactions so that they ultimately match the target reaction as closely as possible. Just to show those manipulations in action a little bit, we have one last example we're going to talk about to go over how we can kind of basically dealing with more complex problems. In this situation, we have a target reaction where dinitrogen tetraoxide is being converted into nitrogen dioxide. This is actually a very classic reaction used to show equilibriums that are based on temperature. As you change the temperature for one of the two things, you can force the reaction to go in one direction or the other. This is something we'll take a look at later in the year. For now, we want to calculate the delta H of this reaction. This is what we're interested in here, is this delta H value, and that's going to be based on data provided from these reactions below. And as you can see by the highlighting that I've done, we've got the two chemicals we're interested in, N2O4 and NO2. We've got them listed down below. We have the NO2 and we have the N2O4. However, what's different this time around is that while the NO4 is in the correct place and we have the correct number of them, the NO2 is not. On the target reaction, NO2 is a product. In our data reaction, it is a reactant. And that's a problem for us because when we combine these two reactions together, they will not match the target. Well, we talked about the idea of manipulation, and what we're hoping to do here is take this first reaction and reverse it. If we reverse it, the reactants become the products, and the products become the reactants. And we'll get a reaction that looks like this. What's important to notice is that the reversing of the reaction made for reversing of the sign of delta H. The negative 152 turned into positive 152. We are now no longer interested in this version of the reaction. I think it's good in these problems to cross this old reaction out so we don't accidentally use it. And we're now left with these two reactions that have been corrected so that hopefully they will match ultimately the target we have up above. So here's those two reactions, the old reaction and the corrected reaction written side by side. We're going to do the same thing we did last time, which is going to be to add the two reactions together to get a big total reaction below. All the reactants combined in one line and all the products combined in one line. Again, we can highlight the two chemicals we're interested in here. These are the ones that are part of our target, and then we want to get rid of everything else. And we can only do that if, say for example, a reactant's on one side and we have the same exact product on the other. These two guys cancel out because it didn't react. We started with nitrogen, we ended with nitrogen. Likewise here, our two oxygens can cancel out and we are indeed left with the target reaction of N2O4 plus 2NO2. Just like we can add the reactions together, we can also add our delta H values together. And we can take the negative 21 and the corrected value for our second reaction there, the positive 152. We can add those two guys together and we get a final delta H for this reaction as positive 131 kilojoules of energy. This is a quick run through. I do not necessarily expect you guys are ready to tackle these problems on their own, especially as they get more challenging. What you should walk away from this is the general concept, the idea of adding reactions together, possibly having to manipulate them so that ultimately they add up to the target. If the reactions add up to the target, then the delta H's add up to the target delta H as well. Just to wrap things up then, a quick list of the things that you should be able to do as a result of what we just talked about. Firstly, you should be able to briefly discuss a variety of ways to determine the delta H of any process. We basically broke it down into two main categories. We can measure delta H using calorimetry, or we can calculate delta H values using a variety of methods, one of which being Hess's law, which we've discussed today. You should also be able to describe and identify things as being state functions or not as state functions. There's a definition that goes along with that, and then we had a couple examples of chemicals that were state functions. More importantly, if you understand what a state function is, you should be able to figure out whether something is a state function or not based on what you understand about that actual variable. Lastly but not least, we could talk about how to apply Hess's law to calculate the delta H of a target reaction based on the delta H values from data reactions. We talked about arranging those data reactions to match the target. When you combine them together, we cross out substances on both sides of the reaction and then ultimately combine those delta H values in the same way we combine the actual reactions themselves. As I already said, you should understand what's going on in that process. During class time, we'll spend a bunch more time getting some more experience with this so you guys are actually comfortable doing these on your own.